Hi everyone, and thank you to join us this week. I'm apologies in advance. We have some technical problems and we miss the recording of the initial of the talk. We only lose the introduction of the speaker, so I will do that for you guys now. The seminar of this week will be held by J.D. Kroth and Nanda Gopal. They will talk about the synchrotron radiation by the slowly rotating fermions. This talk will be given by both speakers. Nanda Gopal will first introduce the essentials for the synchrotron radiation, and then JD will tell us about the numerical results. Let's just hear from them. Thank you again, and apologize for the technical problems.
Whenever a charged particle undergoes a curved path, it produces this type of radiation. And the best way to make a charged particle go through a curved trajectory is to apply a magnetic field. In fact, this was how synchrotron radiation was discovered when high energy electrons were accelerated by a magnetic field inside a circular particle accelerator. So, in experiments inside circular accelerators, it is important to consider the synchrotron radiation losses. Synchrotron radiation also occurs in several natural phenomena, like in accretion disk around black holes, where we have charged particles like electrons or ions, which are spiraling inside a magnetic field. Gamma ray bursts are also speculated to be a source of synchrotron radiation. Now, coming to our work, we studied the synchrotron emission from a charged fermion, which is undergoing rotation, placed in a magnetic field. Now, magnetic field itself imposes a rotation on the charged particle, but here we're imposing an independent rigid rotation on the fermion. So the motivation behind this comes from relativistic heavy ion collisions, where we have two nuclei are bombarded against each other, which results in the production of quark-Gluon plasma. Inside this quark-Gluon plasma, we have fermions, which are in very strong electromagnetic fields. Now, if you look at this figure, you can see that the two nuclei collide against each other with an impact radius B, and this results in the Quark-Gluon plasma to have non-zero angular momentum when the collision happens, when this off-center collision happens. And this is the reason for the high vorticity of the plasma. Now, so there is rotation from the magnetic field as well as the rotation of the medium. The charged particle is in magnetic field in rotating medium. So the rotation due to the medium is not negligible compared to the synchrotron frequency. That's why we are specifically studying the effect of rotation in synchrotron radiation. As we can see from this figure, which was obtained by Dr. Tuchin in the following paper, we can see the vorticity of the Quark-Gluon plasma, represented by capital omega, is compared with the synchrotron frequency omega b, is given by the following formula. And if we can see that the vorticity is not negligible compared to the frequency created by the magnetic field. Now, in our work, we did a simplified model where we just take a single fermion and we assume that in the co-rotating frame of the fermion, the magnetic field is constant and uniform. So this is a much more simplified version than what happens inside the QGP. And so just to make the calculation easier as a first step. Now, when it comes to rotating relativistic system, there is a causality constraint. To understand this causality constraint, we need to look at the speed of a particle which is undergoing rotation. So, which is given by the rotational frequency times the radial distance of the particle. So the speed of a particle increases linearly with the distance from the rotation axis. So at one point, that speed can cross the speed of light, which cannot happen. So this imposes a maximum allowed distance for rotating systems, radial distance for the rotating systems. And this is simply given by plugging in c for the velocity of the particle. So we cannot have the size of the rotating system to exceed this causal boundary of c over omega. It's located at c over omega. Now, quantum mechanically, what this means is that our wave function, we should set boundary conditions such that the wave function vanish at the c over omega. But that is difficult to do for a Dirac spinner, possible but difficult. But in this calculation, we'll use a different assumption, which is that the magnetic length given by the formula shown here, which is the characteristic length beyond which the wave function is suppressed in a magnetic field. So this magnetic length we will take to be much smaller than the size of the causal boundary. And so which means that the boundary is very far away. So we can take the wave function to vanish at large radial distance or in infinity instead of imposing it to vanish at one specific point. To see whether this assumption makes sense, we'll plug in some numbers. So in QGP, the vorticity corresponds to size of the causal boundary to be about 100 Fermis, which is not very big, but the magnetic field achieved in heavy ion collisions are so huge, about 10 to the 4 of the order of 10 to the 14 Teslas, that the magnetic length is even smaller, of the order of only a Fermi. So this assumption makes sense. Now, our analytical procedure can be broken down into 3 steps. First, we solve the Dirac equation for a rotating fermion placed in a magnetic field, and we obtain the energy spectrum and eigenstates. Second step is rather straightforward to find the wave function of the photon in cylindrical coordinates. We'll be using cylindrical coordinates because that's the most convenient one to impose rotation. And the final step is, once we get these wave functions, we can calculate the amplitude of photon emission, and from that, the total radiation intensity. Okay, so let's dive right into the first step, which is to solve the Dirac equation. But before we go to the Dirac equation with rotation, we'll switch off the rotation and see what the solution looks like. So in this case, the Dirac equation is modified by the covariant derivative, which is the usual derivative plus the 4-vector potential term. And also one more thing, we'll be working in units where h cross and c equals 1, and capital M, which is the mass of the fermion, is also set to 1. We'll be working in dimensionless units. We'll assume that the magnetic field is along the c hat direction, and in the symmetric gauge, that will give us the following 4-vector potential. And this gives us, and the solutions are eigenstates of the Hamiltonian, the c component of linear momentum, and the c component of the total angular momentum. So this gives us the relativistic Landau states, Landau levels, and which are characterized by the following quantum numbers: the principal quantum number n, the angular momentum quantum number m, and the continuous quantum number for Tc. We also have zeta, which characterizes the fermion polarization. And now there is one more quantum number, the radial quantum number A, which is not independent of the others. It depends on n and m as shown in the relation as shown. And we'll be working with n and a as the quantum numbers instead of n and m, because n and a are non-negative integers, so it's much more convenient to work with n and a. And the energy spectrum for in this case is given as follows, and we can see that the energy only depends on n and not on m, so there's a degeneracy in m. And the eigenstates are given by the following bispinner, and we can see that in this bispinner there is this function, this I function, and this I function consists of an exponential factor, a power law, and the generalized Laguerre polynomial. And we can see that the exponential factor makes sure that the wave function vanishes off at large enough distance. And in fact, the characteristic length scale of that decay is indeed the magnetic length that we seen earlier. The constants of the wave function are fixed by normalization. Now, coming into the rotating frame, the only difference that rotation brings is in the covariant derivative, is that it adds this term, this gamma mu term, which is related to the Christoffel symbols of this non-inertial frame. What this does in the end is to introduce an additional term in the previous Hamiltonian. Here H naught is the Hamiltonian without rotation. This additional term will be omega dot j. We'll take the rotation vector to be along the z-axis, along the axis of the magnetic field, and that gives us omega jc. So surprisingly, despite the Dirac equation and all the quantum mechanical approach, we have rotation. The effective rotation is just the same as in classical mechanics, and we have seen that the eigenstates of H naught are also eigenstates of Jc, so we can use the same eigenstates as before in this case. And so the only effect is to change the energy spectrum. This term is similar to Siemens splitting in a hydrogen atom. So what it does is just lift the degeneracy over m with this addition. So the energy spectrum change is shifted by this term m omega. And we talked about the causality constraint. So rather than impose the boundary condition that psi vanish at 1 over omega, we'll impose the condition that the expectation value of the radial distance of the wave function, square of the radial distance of the wave function, is much less than the square of the size of the causal boundary. And that gives us the following inequality. So as long as we are in slow rotation domain, omega being very small, b over omega squared will be sufficiently large that we can use reasonable values for n and a. They are allowed. Now we'll be studying spontaneous emission of photons when fermion transitions from one Landau level to another. So that means the energy of the initial fermion will be greater than the energy of the final fermion. Now the second step is to obtain the photon wave function, which is pretty standard. We use the radiation gauge and solve the Maxwell's equation. But the important thing is we'll be solving for the vector potential in cylindrical coordinates, and we will not impose the fermion's rotation on the photon. So we'll be obtaining the photon wave function just in cylindrical coordinates. And so the wave function, we obtain the wave function. It has for a circularly polarized beam, and has the following quantum numbers: h being the helicity, and the angular momentum, and k the momentum. So once we have all the wave function, the next step is to calculate the S matrix. And so we have the wave function of the initial fermion, without the primes, wave function of the final fermion with the primes, and the wave function of the photon. And with that, we calculate the S matrix element, and which gives us the amplitude of photon emission from one specific Landau level to another. So once we have S, integrating and summing over mod S squared over all the final state quantum numbers will give us the probability of radiation, and dividing by total observation time gives us the photon emission rate. So multiplying this with the energy of the photon gives us the differential radiation density. Now, there are several conservations that occur here. But first of all, explicitly shown in the S matrix element is the conservation of energy. So the energy of the initial fermion equals the energy of the final fermion plus that of the photon. The C component of momentum and total angular momentum are also conserved as given by these equations. Here, theta is the angle of emission of the photon. It's the angle the photon makes with the z-axis, or the axis of rotation. Now, once we have the differential radiation density, to get total radiation density, we need to integrate over all omega. And that integral is trivial. We can simply make use of the delta function that was there in the S matrix. And once we massage that a little, we can convert to this simplified form in terms of omega, where omega naught is the value of omega that solves for the argument being 0 on the left-hand side of the equation. Uh, and for in our calculation, we assume that the initial C component of the momentum of the fermion is 0, because we obviously have translational symmetry along the Z-axis. We can always choose boost into a frame such that the initial fermion does not have a C component of momentum. And so once we plug in all the wave function and calculate, we will end up with the total radiation intensity of, for a given initial state fermion undergoing rotation, producing synchrotron radiation. We also had zeta, which is the polarization of the fermion. We need to, so we'll average over the initial polarization states to obtain the total radiation density, and that is shown by this expression. And here, the two gamma terms are what we obtain at the end of what we had in the previous slide. Everything in this integral just boils down to what we have here in terms of gamma. And we can see here that we still have a sum over the final state quantum numbers n prime and a prime, and an integral over the emission angle of photon. This is as far as we can go analytically. Remaining to move forward, we need to use numerical techniques, which JD will explain shortly. So this brings us to the end of the first part of the talk. Are there any questions? Nothing? Yeah.
So, if you could remind me the definition of gamma.
Oh, this gamma?
Yes.
This is a shorthand notation for the final expression that we obtain. So we started with this expression for the S matrix, and when we plug in all the wave function elements and sum over the initial polarization, we get these two terms. These two corresponds to the initial fermion polarization.
So is it like gamma function? Or is it
No, it's not the gamma function. It's a complicated function that just shortened.
If we want to skip to the end,
Yeah, I
we can.
show you the expression.
Yeah.
No, this was one
Yeah.
of the
Spoilers.
Yes, spoiler alert. Yeah, these are the gammas.
Yeah.
Yeah, where the constants are also new. Yeah. Anyway, yeah, it's just a simplified expression for that. Yeah. Any other question? Okay. Then I welcome JD to conclude the talk.
Okay. Thanks for the introduction. That archive link seems to not exist. No idea where that number came from. I will investigate later. So my half of the presentation today will be about talking about the results that we get out of this analytical form, taking it, converting it into some numerical things. And so the things that we were interested in over the summer were what is the frequency spectrum? What energy do these photons have? What's the angular distribution? Where are these photons going? And what's the total intensity once we integrate over omega, add up all the final states, and integrate over theta? How much energy is being put out of here per unit time? And another note, we'll be reporting our results as normalized to the classical intensity, which is important to note that it is proportional to the energy of the photon or the fermion squared. And so there's some, the radiation will seem to decrease at higher energy, but that's just the suppression in that normalization. And so first I'll discuss the frequency spectrum. And so to do this, we're going to actually go back a few slides to the S matrix, and instead of integrating over omega to get the to enforce that the radiated photon has this omega naught frequency, we're going to instead integrate over theta and enforce that it is emitted with a certain theta naught. So given a initial set of quantum numbers and a final set of quantum numbers and a frequency that we want, what is the angle that will be emitted at? And so then we integrate over the theta by using the delta function, and then we see what happens when we choose different parameters. And so doing all that, we get this plot. And so this is a kind of characteristic frequency spectrum. The dashed lines here are the case without any rotation. There isn't one over here into this n prime equals 4 island because it's just kind of off the page. Each final state n prime corresponds essentially to an island of peaks in this spectrum. And what it turns out is that each of these peaks correspond to a specific final a prime value. So because we have lifted the degeneracy in m, represented by having only one line for each n prime, we now have no degeneracy in m or a, and so we have a dependence of the emitted photons on that number. It's also important to note that you can kind of eyeball it here, but these maxima of the peaks are roughly equally spaced. Each spacing is about omega. Each peak is about shifted down by m omega from each non-rotating case. And finally, we only sum over a few of the allowed a primes here. A prime can be any integer as long as our energy or our final energy is less than our initial energy. And so we only sum over a few here, but it's okay because we can see that as this goes down, and this corresponds to increasing a going to the left, we have decreasing amplitudes for each peak. And so there is some dependence on the amplitude of the actual emission on a prime. And so just to reiterate the key points, we break our degeneracy in m. That's something that we can see in the spectrum. Our peaks are shifted down by roughly m omega, and they also get shorter. There was one line that was taller than the rest. That was the no rotation line. And essentially we're splitting that up into many peaks in the case of in the case with rotation. And finally, only certain a prime give significant radiation. And that last point is an important point to make because in that summation over n prime and a prime for our total radiation, n prime has to go up to roughly n. A typical value for the initial quantum number n is a few thousand. But we also need to sum over a prime. Now, in the case of no rotation, that goes up to infinity, and we can do it analytically because there's no dependence on the emitted photon frequency on that quantum number. But here with rotation, there is. And so because of the causality and boundary conditions, we have to cut that off at a prime, roughly a few 100,000. So we have roughly a few thousand n prime peaks or n prime final values times a few 100,000 final a prime values. Multiply those together, and it's a few billion terms in that sum that we had in the previous page. And that presents a significant numerical problem because it's hard to do any of that analytically. And so this is the point I was just trying to make. There are a few billion terms in that sum, and each one of those is an integral, but that's the integral is the least of our problems. So n prime and a prime are essentially bounded by saying our final photon or our final fermion energy is less than our initial fermion energy, and it's also greater than 0. When we sum over n prime, we just go from 0 to n. That's pretty straightforward. That's a few thousand terms. That's nothing. However, if we crank up A prime, and that's down here, is energy is roughly, or goes with minus omega A prime, we can push down the energy enough if we make A prime large to make N prime greater than N, which introduced another whole zoo of terms to add. Investigating this, it seems like the A prime required is very large, which runs up against our essentially boundary condition that we talked about earlier. And also it makes the contributions to the sum very small. So cross that one out. Now all we need to do is sum over A prime until E prime is less than 0. Because omega is small and the energy has a term of minus omega A prime, that's going to happen very slowly. And again, we get a few 100,000 A primes that we have to sum over. And we could do all this, or we'll run into our boundary condition, or this is a consequence of our boundary condition, that our N and A, or N and N prime into A prime, have to be much less than this ratio of lengths. And so to tackle this problem, I looked and investigated what do these contributions actually look like. So if we fix essentially N, A, and N prime, and just take the integral for a bunch of different A primes and plot it, what does it look like? So here we've got about 200 values of A prime. There are a few 100,000 more that I'm not showing you and I didn't calculate. But it looks like there are only about 100 or so terms that we actually want to calculate, or that we might care to calculate, depending on what tolerance we set. And so this is just a kind of characteristic one. If we could narrow a few 100,000 A prime down to 100 A prime for each value of N prime that we're looking at, that would be a great boon to our computational capacity. And so let's look at all this and now vary N prime as well and get a few of these plots. And so these are the same initial parameters, but now we've got multiple N prime here descending from the top, or ascending N prime from the top. And so with N prime is 2,999, so one less than N, we have what looks like one significant A prime contribution. Let's bring it up to 2,500. We've got a few more. Okay. A few more, but kind of shifted over for N is 2,000, and the trend continues down this way. The omega dependence on there is somewhat interesting. It tends to make one of these peaks kind of more lopsided. The B dependence is essentially just changing the amplitude of each. Moves it around slightly, but the same characteristic features are all there. And so as N prime increases, we move things to the left towards, this is with A equals 1, so it's kind of hard to see, or potentially hard to see. This is essentially just A prime is equal to A, or thereabouts. And so we get, again, the comments that I just made. Increasing N prime pushes our sum contributions to the left. N prime equal to approximately N only has significant sum contributions for A, roughly A prime. And our amplitude is somewhat dependent on N prime. We go back here, 10 to the -5, -4, -5, -6, 10 to the -28. That's much smaller. If you look at the more data, you can see that it peaks at roughly N prime is 80% of N. Not sure why. I did look for an analytical form to predict where these things are, but nothing jumped out at me. But it turns out that most of your N's, at least 90% of them, or most of your N prime values do contribute to the sum in a significant way. And another interesting fact that you get is that there are about A+1 of these Gaussian islands on your A prime axis for any given N prime, at least up to resolution, because these are discrete values. And so with that knowledge, we can kind of say, okay, there are only some places that we want to sum. We can't necessarily say, okay, where does it go up and then down, however many times. But this is the summation strategy I came up with. So we're going to start at n prime equals n, where we know where our significant contributions are. We're going to say, let's calculate at theta equals pi over 2. In a few slides, you'll see why I choose that, because it's essentially the maximum of the angular distribution for this guy. And we're going to do that for a bunch of a prime values. We're going to start with a and do plus or minus 10. It could be any integer. We just want to give it some width so that we can capture any movement of these peaks. Now, if these peaks that we calculate are greater than some tolerance, then we are going to do it. It calculates the angular distribution for that term at all angles. Add it to our sum and keep going. Now we're going to make a note of what's the smallest a prime that we did that for, what's the largest a prime that we did that for, and then make a note of that. Use that in our next step where we go to n prime minus 1. We're going to say, okay, we're going to start at the minimum a prime minus 10 or so, and then we're going to go to the maximum a prime plus 10 or so, just to capture the width of the thing. And then we're going to keep doing that, calculate peaks, calculate angles, and iterate until we reach the n prime equal to 0. And so just a graphic of what that's doing. We're going to start down here at 2999 or 3000, draw a box, and we're going to calculate the intensity at pi over 2 at that guy. We're going to say, okay, there's one guy there that meets our tolerance. Let's calculate it for all angles. And then notes, okay, that's our minimum and maximum, and go to the next step. Now we can move over a little bit because we know where that peak was, and say, okay, let's calculate a bunch of peaks. Let's calculate the significant contributions to the sum. Note where the minimum and maximum are. Move to the next step. And in doing this, we can slide ourselves along the axis without getting any of the unimportant or small, any small contributions, because I plot out to a prime is 2500 here, but this axis goes all the way out to the cornfields, few 100,000, like I said, and we get to move along our axis without any significant computational waste. And so using this summation strategy, we can do the rest of our numerical analysis. We're going to start by getting that angular distribution. We're just going to use our final equation that I had on my first slide and on the Gopal's last slide, integrate over omega, and then we're going to use our summation strategy to get all the significant contributions greater than whatever tolerance we want. And then choose n and a, choose b and omega, see what happens. And so this is what we get without rotation. Fairly unremarkable Lorentzian shape. I think this is the limit of what you get in, say, Jackson or something. Now we're going to introduce rotation, which is parallel to the axis. So omega and b are pointing in the same direction. And we see an enhancement at all angles, basically. Same characteristic shape, but enhanced. And now if we have b going this way and omega going this way, we get a suppression by, looks like about the same amount, proportionally. And so this is the big thing, or the first glimpse of the big thing. Rotation with the field gives us an enhancement of the radiation. Rotation against the field gives us suppression of the radiation. We can do this for a smaller magnetic field, one order of magnitude less, and we see the same thing. Just a little bit wider, it's lower energy. And so the key points of that, again, Lorentzian shape, fairly unremarkable, but omega greater than 0 with the field increases radiation, omega less than 0 against the field decreases it. And so now we're just going to get into the total intensity. We're going to use that data that we got for the angular distribution, numerically integrate, and see what happens for various input parameters. And this is the figure we get. So this is the total intensity normalized to classical intensity. Here, or one of these lines here, is our no rotation case. It approaches this dotted line, which is our semi-classical results, essentially in a high energy, where we say n prime goes to a continuum, and we can integrate rather than sum. But the interesting things are these guys, right? So with the same magnitude of rotation, we see enhancement and suppression of roughly the same factor. And for slightly larger rotation, or slightly larger, but still fairly small, at least compared to QB, we get a pretty significant suppression at higher energies. And with this rotation, which is getting closer to saying our approximation is a little bit shaky, we get an almost total suppression even at lower energies. The effect is also considerably larger for larger energies. And these guys are mysteriously going off the page here.
Sorry, Eddie.
Yeah.
So do you have these two lines for different percent? Oh, I didn't see the
Oh.
sign. Sorry. Okay.
Yeah,
My bad.
sign.
Yeah.
Note the sign here, yeah. And so let's look at this guy. So the no rotation case is down here. I will remind you of the scale 1, 1500. Something big is going on here. It may be that our approximation is breaking down a bit, but the same behavior is seen of that 10 to minus 5, omega equals 10 to minus 5 line, except that's a little bit shorter, but it's still increasing. And our numerical results haven't returned a tail like this yet, but there's no reason not to expect it. There's no reason to expect it. Let's go to slightly smaller magnetic field. So these black lines are the smaller magnetic field. These gray lines are the lines I showed you on the last slide, but at a lower energy. The last plot had energy out to 10. This one has it out to 5. That's just because in that dispersion relation we had E is roughly square root of 2n times B. The smaller magnetic field means we need to go to higher n, which means more sum contributions to compute, which means longer computation time. But at this lower energy, we see the same characteristic behavior that we saw on the last slide, or on the last figure, for QB is 10 to minus 2 at higher energy over here. And so the main points to take away from that are that our rotation has a noticeable effect on the synchrotron radiation. For omega greater than 0, we increase the radiation intensity. We saw that with the angular distribution, and of course it carries over into the total. Omega less than 0 suppresses the radiation, and we see a marked increase for greater values of the energy. We also get a large effect for even small omega that we've been assuming we have, and we have qualitatively similar behavior of this effect for all magnetic fields. And so the last thing is we have a bit of a somewhat classical interpretation of this. And so if we've got an electron and we place ourselves in this rotating frame, when we let this electron go with the magnetic field, it's going to start going around in this direction. And so now we want to, or it's going to go around with the synchrotron frequency over there. And so now we want to get out of the rotating frame into our lab frame. And so while the electron is going this way and the frame is rotating in this direction, I'm going to rotate in the opposite direction to get out of it. So my electron is going this way, I'm going to start turning this way, and I see the electron must be going faster because I'm rotating essentially against the electron's rotation. And so it's moving faster, it must be seeing a greater field, it must be radiating more. And that's what we see in the plot that I had a few slides ago. The opposite happens if the rotation is going the opposite direction. The electron's going this way, I'm going to rotate this way to get out of that field, that frame, and the electron looks like it's going more slowly because I'm rotating this way while it's also doing that. And so I say the electron is moving more slowly it must be seeing a smaller field, it must be radiating less. And so that's essentially what we have here, these the QB motion, the synchrotron motion, and the rotating frame motions add up to get larger radiation. In the other case, we have them essentially subtracted. And the energy dependence of that, the falling off, the greater effect at larger energy, is essentially because this synchrotron radiation is equal to or proportional to 1 over the energy. So as the energy increases, this guy is going down while the omega is staying the same. And so omega B is getting smaller while omega is getting larger. And so the effect is enhanced. Now all that I said is essentially the opposite for a positive charge, because this guy is going to reverse. So if we all just turn our heads, we get this guy for positive charges, but this guy with B and omega aligned essentially. For the positive charges, we get a suppression, and with them anti-aligned positive charges, we get a enhancement. And so that essentially brings us into where we are right now. So our current work, Nandagopal's current project, is to say we want to do semi-classics with this. We want to say, or in the no rotation case, we can do semi-classics and say the sum over n prime goes to an integral over n prime, which is much easier to do. And we want to do the same thing with a prime. We want to say sum over a prime goes from the integral over a prime, and then that would significantly cut down on our computation time. Then we want to essentially make more figures like the one that I showed of the total radiation, get more B and omega combinations, see what happens. The problem with this is, again, the slow computation time. We need a better way to sum things, or just go to the semi-classics. This last bullet is less of a problem now than it was when I wrote it 2 weeks ago. But everything I told you on the last slide may have been slightly wrong, because it seemed, without some importantly detailed bookkeeping, it looked like with B pointed this way and omega pointed this way, it was different from having them like this. So essentially, even without rotation, it looked like an electron and a positron in the same magnetic field would be radiating slightly differently, which doesn't seem like it would happen. And likewise, if we had B like this and omega like this, it looked like it was different than this guy. Some kind of charge or parity violating effect. But we think now, since I wrote this, that if we do the detailed bookkeeping and do everything correctly, that doesn't happen, and it's all good. We only have 2 cases of aligned and anti-aligned. And that leads into the future work that we're looking at. We want better boundary conditions. This is something actually that Dr. Vijayakumar and Dr. Tuchin are working on now. But we said omega squared essentially is much less than B. We want to say, what if omega squared is much greater than B? What if it's about the same as B? Because then we have arbitrary omega and we can do more predictions. At least when I saw it, essentially in our I functions way back when, we had those Laguerre polynomials. Those essentially changed to hypergeometric functions, which are famously hard to converge. And then our n values, instead of being integers, they become real numbers that correspond to zeros of the hypergeometric functions. We need to renormalize our wave functions so that it's an incomplete integral over hypergeometric functions. There's got to be a better way. And essentially all that comes from setting the wave function, or rather the current, the radial component of the current equal to 0, and just getting all that out. And then eventually the nuclear physics approach, we want to look at Quark-Gluon Plasma and heavy ion collisions. To do that, we need to get from one fermion to many fermions, which means integrating over the momentum space, integrating over the coordinate space of the plasma, and doing many more computations with the magnetic field as well. And so that concludes the regular part of the talk. There are a few extra slides, though, if anyone is interested.
Is there any questions for the audience here?
Yep.
So you choose which terms to calculate in the sum by looking at, you find a peak at a particular theta array.
Yeah, we go to essentially pi over 2, where this guy lives.
So you have this rotationless expectation, or this is the result. The black curve is from no rotation, right?
Right.
So you expect there to be a peak there. Do you worry that you bias the computation at all by starting, like, only looking at this theta value and not doing a scan of like symmetric points?
Right. There is, I do recall at least one computation where I think lower magnetic fields tends to spread this out. Lower magnetic field and higher energy tends to spread this out a little bit. But so far, it doesn't look like that's occurring. Essentially, just need to look at it, more data, more cases. But it seems like a pretty good strategy so far.
So this thing always has a peak in the middle.
Yeah, and even if it isn't sharply peaked like this, it's, you know, more softly peaked. So it's a good indicator of how we do things, of how the sum is going. Yeah.
Can you go forward a few slides?
Yep.
So did you mention why? Did you know why some of these almost exponentially start to increase when this omega becomes small?
Becomes
Well, when omega
yeah.
there decreases, right? It looks almost like no, it increases. Sorry.
Yeah. Not particularly. It's kind of just it comes out of the numerical approximates that way. I mean, if you stare at this, if you plot essentially the ratios of these, like this curve to this curve and this curve to this curve, they follow roughly the same line, which is about exponential. But if it's, or it looks exponential, but anything concave up looks exponential. But
So I mean, if you were to guess, if you just keep increasing this, you think it will still increase exponentially? That would be.
I don't think so, based on at least this guy. You know, it shoots up, but then it starts to come down almost exponentially. Just eyeballing it.
Yeah, but I mean the peak though.
Of right here. Or,
Right, I mean the peak of every curve, right? If you
Right.
keep increasing omega, will it still keep increasing exponentially the peak?
That's a good question. We haven't gone much higher than this because we're running up against
Yeah, sure.
B there, but it's something to look into, and we could do it the other way as well. Is it continuing to get suppressed like that?
Right.
So.
So it looks like minus that minus 3, and then minus 3, like is plus or minus a bit. Can you, I don't know, is it possible like to match this curve by, I don't know, like rescaling E multiplying? Like, is it roughly the same shape?
It is, yeah, I think so. Roughly, I mean, you know, I just showed this next slide.
Yeah.
You know,
if you scale this down, would it match this minus?
potentially, that's again something to look at. Roughly, like I just said, roughly the ratios of these guys to the non-rotating case do follow the same path, even though they aren't exactly the same. But
We'll try to find shape.
yeah.
Not successfully, but
Yeah. It's an open question. It is the answer, I think.
But we yeah, because you have these curves, you can just.
Yeah. I haven't applied any fitting functions to it yet, but.
No, I mean like just once.
Oh, sure. I haven't done anything with that yet, but good suggestion. Yeah.
Yeah, so I mean, at the end, the goal is apply this to Quark-Gluon Plasma, right?
Mhm.
So your geometry now is you're assuming that you have a cylinder, right?
Right.
So even before going beyond that,
Mhm.
can we ask how complicated it would be to go a little further by implementing this football shape that the QEG plasma has when it starts to rotating? I mean, in a simple way, right?
Mhm.
Because this is just, you are assuming this
Right.
cylinder core, just assuming that kind
Yeah.
of spherical.
Yeah. That's not something that I'm very knowledgeable about, but I imagine if I'm just imagining this in a very simple model, we could just say we have many of these identical fermions with a locally constant magnetic field, and then just integrate over some density function in position space is like my first naive order model or zeroth order model.
That's something that could work.
Mhm.
Is there any question from? Oh, sorry.
Yeah, I was just clarification. Like, what exactly did like the A's and A prime refer to?
A and A prime were those quantum numbers we had closer to the beginning, essentially just related to this n and m, the angular momentum number and the principal number, just a way to rescale things. Yeah.
Is there any physically significant when when W becomes equal W equal to W plus T?
That's essentially the high energy limit. Here it's a little bit easier to see with a smaller magnetic field, more classical kind of, but it is kind of approaching this one limit. It just means it's approaching the classical case.
What happens when it exceeds?
That means that we're getting enhancement of the radiation, essentially just beyond what the classical thing says.
Is there any question from some audience? Well, if we don't have more questions, we thank again to the speakers. And now, apologize again for getting the recording.